Hello viewers, in this session we are going to talk about the total derivatives. Now the concept of total derivatives extends the notion of ordinary derivatives from a single variable function to a multivariable function. This offers a deep insight into how these functions behave in multiple dimensions. So understanding total derivatives is important, especially in economics and other fields such as engineering, because some of these functions, especially in, for example, in economics, that relates economic models, often depends on multiple variables, and analyzing their behavior requires a comprehensive knowledge of their rate of change with respect to each of the variable independently and collectively. Through the study of total derivatives, one gains a powerful tool for analyzing intricate relationship between variables within multivariable functions, facilitating precise predictions and interpretations in diverse real-world scenarios. So let's consider a function of two variables. Z is a function of two variables, x and y. So here, x and y are independent variables. Then the total derivative dz is given as dz is equals to the partial derivative of z with respect to x times dx plus the partial derivative of z with respect to y times dy. So basically it's a sum of the partial derivatives. So the total derivative, the total differential dz is a tool that can help us understand how a change in one variable affects the overall outcome, which is represented by z, considering changes in all influencing factors. So let's take an example. So we have a function of two variables given by z is equals to x cubed y squared plus 2xy cubed. And we want to find dz by dx along the parabola defined by y is equals to 3x squared minus 5. So we have seen that the total derivative dz is expressed as the partial derivative of z with respect to x times dx plus the partial derivative of z with respect to y times dy. So if we want to find dz dx, we simply divide both sides by dx. So in this case, we have dz by dx is equals to the partial derivative of z with respect to x times dx divided by dx plus the partial derivative of z with respect to y times dy divided by dx. In this case, this dx here is 1. So we get the partial derivative of z with respect to x plus the partial derivative of z with respect to y times dy by dx. So in this case, we have the function z here. So we can differentiate z partially with respect to x, and we can also differentiate z partially with respect to y. So since z is equals to x cubed y squared plus 2, so z is equals to, we have z is equals to x cubed y squared plus 2x, 2xy cubed. So if we want to find the partial derivative of z with respect to x, then we hold y constant, so we write y squared, then we differentiate with respect to x, x cubed, plus 2y cubed, then we differentiate with respect to x, the quantity x. So in this case, the first term will give us y squared times 3x squared. The second term will give us 2y cubed. times 1, which is 3x squared y squared plus 2y cubed. This is the first order partial derivative of y, of z, sorry, with respect to x. This is y squared. So similarly, we can find the first order partial derivative of z with respect to y by again taking the same function, but this time differentiating. So we have again z is equals to x cubed y squared plus 2x y cubed. This time, if we want to find the partial derivative of z with respect to y, then we shall treat x as a constant. So the first time we write x cubed, then the derivative of y squared with respect to y, and in the second term we write 2x, then the derivative with respect to y of y cubed. So when we work out this, the first time we get x cubed, then times 2y, and in the second term we have 2x multiplying 3y squared. So that we get 2x cubed y plus 6x y squared, which is the first order partial derivative of z with respect to y. So let's look at what we have. In our expression, we have the partial derivative of z with respect to x. We have the partial derivative of z with respect to y. Those ones we have obtained here. But then we have dy dx. But now we have the relationship between x and y. Y is equals to 3x squared minus 5. So we have y is equals to 3x squared minus 5. So this we can therefore differentiate y with respect to x to get 6x. So now that we have everything that we required in our expression, the rest is just to substitute, and we get our function there, dz by dx. This is the derivative of z with respect to x in the direction of the given parabola. We have a second example here. U is x raised to power 5, y raised to power plus y raised to power 5. And you are given the relationship between x and y. X squared plus y squared is equals to 9. And the problem is to find du dx. Now we see that u is a function of x and y, again here. So we can write du is equals to the partial derivative of u with respect to x times dx plus the partial derivative of u with respect to y times dy. We then divide here by dx. We divide through by dx. And this quantity here is 1. So we end up with this expression. And now we have u is x raised to power 5 plus y raised to power 5. So when we find the partial derivative of u with respect to x, we get 5x raised to power 4. And the derivative of u with respect to y, the partial derivative, is 5y raised to the power of 4. Next, we want to find dy dx. We are given that x squared plus y squared is equals to 9. So if we differentiate both sides with respect to x, these are not partial derivatives, so we are not assuming that y is a constant or x is a constant here. These are the ordinary derivatives which are total. So to differentiate x squared with respect to x, that will just give us 2x. But to differentiate y squared, we shall use what we call the chain rule. So we differentiate with respect to y squared, then we multiply by dy dx. Then the other side we have the derivative of a constant is 0. So that in this case we get 2x plus 2y dy by dx is equals to 0, or 2y dy dx is equals to minus 2x, and therefore dy dx can be obtained by dividing both sides by 2y, which will give us minus x divided by y. So this is dy dx minus x divided by y. So the rest is now to substitute back, and we get this expression. Now we have another example here. The base radius r of a right circular cone is increasing at the rate of 1.5 centimeters per second, while the perpendicular height is decreasing at the rate of 1.2 centimeters per second. The problem is to find the rate at which the volume is changing at an instant when r is 3 centimeters and h is 5 centimeters. Remember, when you have a cone of base radius r and perpendicular height h, the perpendicular height h here, the base radius is r, then the volume is given by 1 over 3 pi r squared times h. So it's a function of two variables. Volume is a function of two variables, which are r and h. So we are given that the rate at which r is changing, the rate of change of r per unit change in time, you're told that r is increasing. So there's a positive rate of change at 1.5 centimeters per second. 2, the rate at which the perpendicular height is changing per unit time. If we go back there, we see that the height is decreasing. So this is a negative rate of change of 1.2. So we have minus 1.2 centimeters per second. So dr by dt and h by dt are as given there. Then we have that since we have said the volume here is a function of r and h, that means that we can find the total derivative dv, which is can be expressed as the partial derivative of v with respect to r times dr plus the partial derivative of v with respect to h times dh. Since we want to find the rate at which the volume changes per unit change in time, that is dv by dt, then we shall divide both sides of this expression by dt, so that we have the partial derivative of v with respect to r times dr by dt plus the partial derivative of v with respect to h times dh by dt. Now we know the values of dr dt and dh dt. We also know the volume of a cone is given by 1 over 3 pi r squared times h, meaning that we can differentiate v partially with respect to r to get 2 over 3 pi rh, and we can also differentiate v with respect to h to get 1 over 3 pi r squared. So the rest now is to substitute. The rest is to substitute. The partial derivative of v with respect to r is 2 over 3 pi rh, and the partial derivative of v with respect to h is 1 over 3 pi r squared. Then dr dt, we had those quantities here. dr dt is 1.5, dh dt is negative 1.2. So we substitute. This is the partial derivative of r with the rest of v with respect to r. This is the partial derivative of v with respect to h. So 1.5 is dr dt minus 1.2 is dh dt. So when we simplify, we get dv dt is equals to minus pi rh, plus pi rh minus 0.4 pi r squared. But we want to find the value of this when r is equals to 3 centimeters and h is 5 centimeters. So substituting r is 3 and h is 5 in this expression, we get 35.81 cubic centimeters per second. We notice that this rate of change is positive, and this means that the volume of the cone is increasing. The volume is increasing at the rate of 35.81 cubic centimeters per second. Now we have a similar question here in a mining industry concern. A conveyor belt delivers waste product onto a waste pile at the rate of 0.025 cubic meters per second. And then you're told that the waste forms a conical heap whose height is equal to its base radius. The problem is to determine the rate at which the height is increasing when the volume of the cone formed by this waste is 2 cubic meters. So this one can be done in a similar way. We just need to write again v is equals to 1 over 3 pi r squared h. So the partial derivative of v with respect to r is equals to 2 over 3 pi r h, and the partial derivative of v with respect to h is equals to 1 over 3 pi r squared, as we had seen in the previous example. So the total derivative dv can be expressed as the partial derivative dv dr times dr plus the partial derivative dv dh times dh. So that when we divide this side by dt, we divide through by dt, we get the rate of change of v per unit change in time. Now, there is some additional information here that the waste product forms a conical heap whose height is equal to its base radius. Whose height is equal to its base radius. So h is equal to r in this expression. Meaning that the volume, which we have expressed as 1 over 3 pi r squared h, we can write it as, we can substitute r is equal to h. We can, depending on the question, determine the rate at which the height is increasing, because we want to determine the height. So we write r is equal to h, because r is the base radius is equal to height. So this will be 1 over 3 pi r cubed pi h squared times h, which will give us 1 over 3 pi h cubed. So the volume can be expressed in this form. Also, the partial derivative that we have written as the partial derivative of v with respect to r, which was 2 over 3 pi r h, can now be expressed as 2 over 3 pi h squared, and the partial derivative of v with respect to h, which was 1 over 3 pi r squared, we can now write 1 over 3 pi h squared, since r is equal to h. So in our expression here, in our expression here, we shall substitute the partial derivative of v with respect to r and the partial derivative of v with respect to h as we have there. Then dr dt is equals to dh dt. So we can write in our expression where we had dv by dt is equals to the partial derivative of v with respect to r times dr by dt plus the partial derivative of v with respect to h times dh by dt. When we substitute the expressions here, we can write 2 all over 3 pi h squared times dh by dt, because the rate at which the height changes is equals to the rate at which the radius changes, plus 1 over 3 pi h squared dh by dt. And in this case, we see this when we simplify, we get pi h squared dh by dt. This is dv by dt. Then the information given here is that the rate at which the volume is changing is this 0.025 cubic meters. So we can substitute here and write 0.025 is equals to pi h squared dh by dt. Since we are looking for dh by dt, then we write dh by dt is equals to 0.025 divided by pi h squared. This is the rate at which the height is changing at any time t. But we want to find the rate when the volume V is equals to 2.0 cubic meters. Remember, V is given by pi all over 3 r squared h, which we can write as 1 all over 3 pi h cubed. This is 2.0 pi h cubed because r is equals to h. So in this case, we can write h cubed is equals to 2 times 3 all over pi, or this is 6 all over pi. So h will be the cube root of this. H will be the cube root of 6 divided by pi. This is the value of h. Once we know the value of h, and we have our expression here, then we can write dh dt, dh by dt, which is 0.025 divided by pi h squared, will now be equals to 0.025 divided by pi times the cube root of 6 divided by pi raised to the power of 2. So working out this should give us the value, the rate at which the height changes per unit change in time. We say the quantity is positive, indicating that the height is increasing. The height is increasing. So this, we can compute that and get the value. So basically, these are the kind of problems we can easily solve using the idea of total derivatives. So in the next video, we're going to look at the application of total derivatives to find differentiation of, to find the derivative of implicit function. So thank you for watching and have a good day.